And let me start by greeting everyone. It's really a pleasure to be here, although I was much more love to be there. But let me thank the organizers for this opportunity to present some work that I've been doing over the years with many collaborators, a list of which, partial list, I should say, you can see on the screen, and about these bosonic stars, their dynamics. And there's a lot of interplays with many different things. Um, I think these object bosonic stars, in my view, are quite interesting for a variety of reasons. They've given rise by now to a considerable literature. Therefore, I can only tell you about a few things, and these are clearly biased by my own work and research interests, but hopefully they will nonetheless convey some notion of the literature. Well, I should also like to thank the organizers, of course, for having me again, and it's really a pleasure to share a little bit of these research interests with all of you. So one of the reasons why these bosonic stars are interesting is that they provide us with a clear departure from a simple paradigm one constructs from the most elementary model in strong gravity. And so this is precisely the observation I would like to start with. There's a paradigm that typically one uses to build an intuition and a vision about any given topic. But paradigms make us develop a sort of a tunnel vision syndrome because our understanding, and in this particular case concerning compact objects, is based, or if you prefer, it's biased by them. So let me be a bit concrete. When we first learned about black holes, the most compact objects in the universe, in general relativity, we discussed them typically in the context of Einstein-Maxwell theory, that's electrovacuum. And of course, that's for a good reason. This is a really nice model in which the stationary and axisymmetric black hole solutions are analytic. Actually, the model is integrable. It can be cast as a nonlinear sigma model, and there's a lot of very nice solution generating techniques you can use to generate solutions given a seed solution. It also turns out that there are no solitons in this model that is stationary, localized, asymptotically flat, everywhere regular, horizonless, lumps of energy. There's some shortcomings in the proofs, I mean, but generically, I think this is kind of accepted. There's also uniqueness theorems for black holes. So the most general solution, the Kerr-Newman solution, has no hair. It has only four macroscopic parameters: the mass, the angular momentum, the electric and magnetic charges. Although these two last ones are generically thought to be astrophysically of little relevance. Of more academic interest, perhaps, but still of a kind of interest for strong gravity as a discipline, there are no balanced neutral two black hole systems that are regular on and outside the horizon. There is indeed a multi-black hole solution, the Majumdar-Papapetrov solution, but it requires charge, electric charge, and in fact, extremal black holes and no spin. Nothing of this really changes if instead of one Maxwell field, you have two or multiple. Note that having two is actually equivalent to have a complex Maxwell field. But a dramatic change occurs if you add a mass term to that complex Maxwell field. Then you have a complex Proca field. And the novelty here parallels very closely what you see for a model where this complex Proca is replaced by a complex massive scalar field, which could have self-interactions but needs not to. So this is the Einstein massive complex Klein-Gordon system. Now, if you look at these models, either of them, the downside is mathematical. The mass term is an obstacle for the integrability structure. And moreover, even in simple spherically symmetric cases, if you want these massive bosonic fields to be non-trivial, excited, the solutions are typically numerical only. But the upside is physical. There is now a rich landscape of solitons called bosonic stars, exhibiting sometimes dynamical surprises, and this is one of the things I would like to tell you about today. But before I actually go into that, I would like to make two other brief points. Firstly, related to the existence of these bosonic stars, scalar or vector, depending if we are in the scalar Klein-Gordon model or the Broca model, there's also this interesting phenomenon of superradiance. And when you have a massive field like this, there's a superradiant instability of rotating black holes. And there's new hairy black holes related to that, and there's a related non-uniqueness. So the first example of this large family of black hole solutions was found about 10 years ago in this paper, and is an example of black holes with scalar hair in general relativity and with matter obeying all important energy conditions, and moreover with a physical formation mechanism, which could be superradiance. So I would just like to make the point that when you hear that black holes have no hair in general relativity, one should be careful and be skeptical. They have no hair in the sense that's typically used in electrovacuum, that's true, but they can have hair in general relativity. And moreover, you can have hair which could have, some interesting dynamics. Now, the second point, as another contrast to the paradigmatic case, is that there are also asymptotically flat, balanced, neutral black holes in these sort of models. And a recent result was obtained in this paper here, which was published last September in PRL, where we show the hair, which can be seen as a kind of boson star environment around the horizon, can provide a physical mechanism to balance two neutral, asymptotically flat, spinning black holes without conical singularities on and outside the horizon. So this was a kind of an old problem in general relativity. The question in vacuum was open, and some people would say that maybe it's still a little bit open. Anyway, so for these double balanced black holes I've just mentioned, as well as the hairy black holes, which are indeed the kind of constituents of this composite system, the bosonic stars play a crucial role. And this is just a point I would like to make in relation to black holes, because my talk will be mostly devoted to the solitons. So, and this is really the goal of my talk, to tell you about something about this landscape of solitons in this class of models. So I would like to tell you a bit more about these bosonic stars. And everything I'm going to say here is, well, in general relativity. So in fact, from the gravity perspective, these bosonic stars appear in general relativity. By this, I mean it's not modified gravity, albeit they are generalizable to modified gravity. So if you have, these bosonic fields that are non-minimally coupled, or you have, modification in the pure gravity sector, you can have this type of solutions as well. But these ones appear in general relativity with simple and physically reasonable matter sources, just a complex, massive scalar field or vector field, complex, massive, so a Broca field, possibly with self-interactions, but certainly with a master. So these two classical effective field theories that I'm showing in this slide stand out on a simplicity criterion, but are by no means exhaustive. The corresponding solitonic solutions are called scalar boson stars in the first case, or vector boson stars, also called Broca stars in the second case. Collectively, sometimes they are called bosonic stars, encompassing both the scalar and vector case. In both cases, the field mass parameter, mu, which you see here, determines also the maximal mass of the stars, and I'll show you how that works, and can be faced as a new scale. So often in the following, I will call these the reference model, simply because they are the simplest. But remember, these type of solutions emerge in many other more complicated models. One can also give bosonic stars a more microscopic perspective. They are often described as a Bose-Einstein condensate of many ultralight particles in the same quantum state, therefore justifying the classical description, meaning you are dealing with a system that the typical action is much, much larger than h bar. The need for ultralightness comes from the existence of a model-dependent maximal mass that I've just mentioned in the previous slide for these bosonic stars. And when I say maximal mass, I mean a maximal ADM mass. So this is the typical scaling for that ADM mass of the star, which goes as 10 to the minus 19 solar masses times the inverse of the particle's mass in giga-electron volt. Thus, for bosonic stars with masses in the astrophysical black hole range, so that, for example, they could mimic black holes, the fundamental bosonic particle must have an ultralight mass within this range that you see here, 10 to the minus 10 to 10 to the minus 20 electron volts. Now, if such hypothetical particles have feeble or no interactions with standard model constituents, they are fuzzy dark matter and likely only detectable gravitationally. Of course, a very important question is, what is their high energy physics origin? How can you have such light masses in a consistent model and protected from all sorts of corrections? So a possible origin is the so-called string axiverse, and this has been debated for over a decade now. But there's also simpler extensions of the standard model where they could appear, and that was discussed in a paper that was done here in collaboration with some particle physicists and also a group in Valencia and other places. So I would suggest you to take a look to see some possible high energy physics models where these things could emerge. Okay, so let's look a little bit at the simplest possible solutions of spherical boson stars or bosonic stars to encompass both the scalar and the vector model. So the simplest ones are spherically symmetric, as you could guess. Now, when you do the ansatz for either the scalar field, which is a complex field, or the vector field, a complex vector field, you always introduce a kind of an amplitude that has a radial dependence only, but crucially, this has this harmonic time dependence that introduces the frequency small omega. And this frequency determines the mass of the solution. So you can see in these two plots for the scalar on the left and for the vector on the right, the ADM mass of the solutions in units of mu, the scalar field mass, versus the frequency of this harmonic time dependence. Now, the solutions, they fall into this red solid line in either case. It's very similar in the scalar and the vector case. So just look at the red solid line. And there's this typical spiraling shape that appears when you calculate the space of solution. Often we call it the domain of existence. And well, you can ask many questions about how each of these solutions, so each point there is a solution, it's a spherical star. How are the physical properties? Well, one important physical properties is their stability. Well, are these solutions any stable? And what has been known and for many years is that when you study linearized radial perturbations of the coupled matter gravity system, there is an unstable mode that arises precisely at the maximum of the ADM mass. These are the simplest, what's called the fundamental family of solutions, meaning they have no the minimum number of nodes for the radial function in spherical symmetry. And so what people have seen then, based on this evidence or thought, is that to the right of this maximal ADM mass solution, there's a stable branch of solutions. And then so this is from the maximal frequency until the maximum ADM mass, and then the other ones are unstable against radial perturbations. And in fact, it's known what occurs to them, to the unstable solutions when they are perturbed. Some migrate to the stable branch, some collapse into black holes, and some disperse altogether in a fission-like event. And there's been a complete analogy between both the scalar and the vector bosonic stars in this understanding of this type of radial stability. Now, the conclusion that there's a stable branch of these spherical bosonic stars was reinforced by two other analyses. First, these stable bosonic stars, spherical ones, both in the scalar and the vector case, were seen to approximately form dynamically from generic dilute initial data. So there's a mechanism for formation. That's very important. So here's the classical illustration by Seidel and Swen from the 1990s. And this is for the case of the scalar stars, but that has been repeated for vector stars. So you start with a coherent complex scalar field with a Gaussian distribution. And one observes that under its own weight, this field, the scalar or the vector field, kind of collapses. It's an incomplete collapse. You don't form a horizon. But there is accompanying this incomplete gravitational collapse, a relaxation mechanism that has been called gravitational cooling. And there is an ejected scalar field radiation. It's not really radiation because it's a massive field, but and this is carrying the excess kinetic energy away such that a more compact object can form and virialize. Thus, the evolution leads to a kind of a perturbed, more compact object, the scalar boson star, with mass below the maximal mass of the model, even though we started with a total bosonic mass in the initial data above the maximal mass of the model. And the result holds for generic initial data, albeit here we are restricting to spherical symmetry, and there is therefore no gravitational wave emission. And also, because these bosonic stars, both the scalar and the vector, were seen to be perturbatively stable against spherical perturbations and to form, as I've just described, they also started to be evolved alone or in binaries, producing waveforms for at least a decade. And as an illustration, what you can see here is the first orbital merger of two spherical vector boson stars. This was done a few years ago already. These simulations were typically quite short and doing head-on collisions or with some momentum transverse to the separation so that they could get a little bit of an orbital motion and not just a head-on collision. And they are done with numerical relativity techniques, which are under control for this case, which is very nice. And sometimes people say, and rightfully so, it's even easier than fluids for various reasons. And for instance, you can use the Einstein toolkit. It's open to the community, and there are thorns now that have already encoded the equations for this type of matter content and the modified Einstein equations, well, that is with the right energy momentum tensor. So accordingly, everything seemed to agree these spherical stars in the right branch are stable. And one of the things that I would like to tell you about today is that this is not so. Well, recently we found that there's actually a very important difference between the scalar and the vector case. And this was a dynamical surprise. It turns out that the spherical vector stars, these are called mini protostars. Mini means that the potential doesn't have any self-interactions here. That these spherical protostars are unstable, but only against non-spherical perturbations. And this is, I thought, a very interesting, surprising result. It was reported in this paper here. And I would like to tell you about it. But before I discuss it, let me revisit the scalar case and tell you another feature about these bosonic stars. Unlike black holes, static black holes in Einstein-Maxwell, that we know are actually spherical by Israel's theorem, bosonic stars can have a multipolar distribution. And this was first seen for the scalar model of mini boson stars. So here's the morphology of the angular distribution, and it is essentially determined by one leading real spherical harmonic. And let me tell you a way to think about these solutions, which again, they are static as a metric. There's always the harmonic time dependence in the amplitude, but in terms of the physical quantities, they are always static. There's a time-like Killing vector field everywhere. Now, the way to think about these solutions could be the following. Now, in flat spacetime, the free, massive Klein-Gordon equation admits this type of solution, where there's a harmonic time dependence, y are the real spherical harmonics, and r is a radial function. It's written then in terms of this modified Bessel function of the first kind. Now, this solution is in flat space for the Klein-Gordon equation, and it's not regular. It diverges at the origin. But minimally coupling this Klein-Gordon field to gravity and turning on gravity regularizes these solutions. And their nonlinear self-gravitating versions for the different choices of the spherical harmonic are these multipolar stars that you see here. So the last two numbers in this trio, so each next to each kind of figure, you have a phi, a scalar field with three numbers, and the last two numbers are the L and the M of the corresponding spherical harmonic that you can see very clearly if you turn off gravity. So these here are the monopolar stars, these are the dipolar, these are the quadrupolar, and so on. And there is a clear hydrogen orbitals-like morphology. And like in hydrogen, the energy you expect is larger for larger quantum numbers, as is illustrated here for this spherical, that is the monopolar, the dipolar, and the quadrupolar families of stars. So each of these curves is the family of one type of those stars. And you see that the energy, in this case, the mass for the same frequency goes up as you go into higher multipoles. A difference with the orbitals in quantum mechanics is, of course, that each choice of the multipolar structure, YLM, gives rise to a continuous set of solutions. There's a family of solutions which exists for a frequency interval rather than a single frequency arising as energy quantization, which is what occurs in quantum mechanics. But fixing the frequency, one clearly sees that the higher multipolar stars have higher energy. Okay, but when you try to do the same construction with protostars, you find something different. So here are the masses along the space of solutions for the spherical case, that is the monopolar stars. This is the dashed black line. For the dipolar case, which turn out to have a prolate morphology, that's the blue solid line, and the quadrupolar case, which turn out to have two separate energy lumps, which is the red solid line. And there are two remarkable features here. First, fixing the frequency. The lowest energy configuration for the frequencies where the stable branch of mini protostars was thought to be is not the monopolar star, but rather the dipolar star that has lower mass. In fact, even the quadrupolar stars can have smaller masses, energies. And this is energetic evidence that the spherical stars are not the ground state of this mini proca family. And we were quite puzzled with this result. So, of course, I mean, the true discriminator of stability should be dynamics. We've given some other evidence for the prolate stars being the ground state, but I will not go into all the details. I will show you some dynamical results coming out from fully three-dimensional simulations using numerical relativity and the Einstein toolkit, and the machinery that was developed in previous works, the example, the one that is quoted, the second reference. So we tried with this to address a number of questions. Here's the first. If the dipolar protostars are the ground state, are they stable in the long-term numerical evolution? So for testing this, what we've done was to select a number of solutions, which we identified as 1 to 4 in this slide, along the blue solid line. So these are prolate protostars, and we've evolved them. And here I'm illustrating evolutions with solution number 3. The other ones are similar. And these evolutions impose no symmetries. So you have to perform fully 3D evolutions, and this was actually a problem before. But anyway, on the left-hand side, you will see, this is going to be a movie, the imaginary part of the Proca scalar potential. Well, that's essentially the AT component of the Proca potential, okay? On the right-hand side, you see the energy density. Now, these evolutions run to around 20,000 in units of the Proca mass. So they are fairly long-term evolutions. And on the left, one sees sometimes the change in colors corresponding to the phase at which the snapshot is taken. This is just phase dynamics. On the right-hand side, we see no evolution. On the energy distribution, which you can approximately see, it's prolate, it's not spherical. So no sign of instability is found, and the same occurs for all solutions studied. So prolate Proca stars in the right frequency interval are dynamically robust, at least in these fairly long timescales. So we pose a second question. If the dipolar Proca stars are the ground state, are spherical stars unstable? And then again, we selected a number of solutions identified in this slide from 5 to 8. So this is along the black dotted dashed line for the spherical stars, the monopolar stars. And choosing these solutions, we've evolved them. Let me illustrate again these evolutions with one of them. This is number 7, doesn't really matter. Again, on the left-hand side, you see the imaginary part of the Proca scalar potential, and on the right side, you see the energy density, which you can see now is round, is spherical. So I'll show it.
Yeah, there is one question. If I interrupt you and tell, one body has asked, can you please clarify how the stability of the perturbation depend on the maximum ADM mass again, please, if it is just...
Yes. So we know that beyond the maximum, these spherical stars are already perturbatively unstable against spherical modes. And for the scalar and the vector case, both of them, we know the spherical modes do not exhibit any instability. What I'm trying to make the case now is that in the case of the vector, that is Proca stars, even though there is no instability in the spherical sector, there is a non-spherical instability, which only seems to happen in the vector case. And this happens even before you reach the maximum mass solution. So all of these spherical vector stars that were thought to be the fundamental state are actually unstable, and they decay to another state, which is the true fundamental state, and it is not spherical. Okay. I hope this clarified. Yeah, thank you so much. Sure. So feel free to, at any point, interrupt me. And anyway, so I will show this again. So then what you're seeing here is that at some point during the evolution, around 2000 or so, changes become visible. And the stars, I'm showing again, ceases to be spherical, seems to develop a prolate kind of morphology, simultaneously getting a kick in the Z direction. This supports the hypothesis that they are decaying into these dipolar prolate stars. The kick also seems to be generic, and this is related to a change in the center of mass, and there is an accompanying emission of Proca field and also radiation that carries momentum in the other direction. The decay from the spherical to prolate solutions, with the first actually being an even parity and the second being an off parity solution in terms of the matter field, seems to turn on this momentum turn in the metric that always triggers this kick. So overall, we found that there's a rich dynamics in the model. In some simulations, we try to block the decay channel into the prolate stars by simply imposing a Z2 symmetry. So the Z2 symmetry would kill the prolate solution because the Broca field is Z2 odd rather than Z2 even. And so you impose a north-south symmetry. But even then, the spherical stars, well, they get some dynamics in which they seem to decay into an intermediate quadrupolar state and then decay into a prolate state, but oriented rather than in the north-south, in the east-west. So the kind of system finds a way to circumvent the symmetry that was imposed, although this imposition does mitigate the instability, and it seems to make it take longer to occur. Anyway, the all evidence supports that these dipolar stars are really the ground state. Now, you could also reconsider what happens if we now evolve this dilute cloud of spherical Broca field, that is this gravitational cooling mechanism of formation that we've seen before, that was done in spherical symmetry, but without imposing spherical symmetry. So you start with something which is spherical, you let it evolve, but in your computer, you're not imposing spherical symmetry. You're doing a full 3D simulation. Now, what happens is indeed that imposing no symmetries, one clearly observes in the collapse of the spherical cloud, the breakdown of the spherical symmetry. And again, hints, although these simulations never reach a final equilibrium state, of a dipolar structure, as you can see in this kind of final snapshot, oriented in some direction, in this case at 45 degrees. So our conclusion is that the Broca model in the static sector has a non-spherical ground state, and the spherical solutions of mini Broca stars considered up to now or up to recently as the ground state are actually unstable against non-spherical dynamics. So there's some comments why this was, for instance, missed before, because some of these evolutions did not actually impose too much symmetry. It's an interesting example because you are saying that staticity and stability are actually implying non-sphericity, which is like, you know, the opposite somehow of Israel's theorem for black holes. These objects can be very compact, by the way, and that's why it's interesting. And also there are other interesting systems where spherical configurations can decay into non-spherical ones in more basic physics, if you're interested, like a charged liquid drop, which was studied by Lord Rayleigh back in the day, in the 19th century. I should also say that there were some results in the Newtonian regime that were already hinting at this the non-stability of the spherical Broca stars. But the most surprising result, perhaps, is precisely in the compact relativistic regime, because our intuition from black holes is typically that as you get more compact, things become more constrained. And if you have some static system, it becomes rounded.
Carlos, there is another question.
Please.
So the question is, it may be a naive question, but it is unclear to me what stellar topologies do the multipolar solitons correspond to physical?
Topology here is always trivial in the sense that, so topology of space-time. If you ask what is the topology of surfaces of constant energy density, say, that can be complicated and it can vary. So sufficiently in some regions and for some values of this energy density, it will coincide with your intuition of spherical harmonics, but it needs not to be so for all values of the energy density. But let me emphasize, in terms of space-time, topology is trivial, okay? So there's no non-trivial topology here. These are non-topological solitons. But of course, the morphology can be complicated. I hope that this answered the question. Otherwise, we can come back to it at the end.
Yeah, okay. Yeah, okay.
Thank you so much. Thank you. Okay, so you may be wondering, though, if this result impacts for the rotating Broca stars. Because I've been dealing with static stars. They don't rotate. They don't have angular momentum. And here there's an interesting story, because the spherical protostars that I've mentioned early on that were thought to be the ground state, but they are not, they were found to having one radial node in the temporal component of the Broca potential. Now, the number of radial nodes typically is describing a sort of excitation, like in hydrogen, radial nodes of the wave function. But curiously, the spherical stars had one radial node. At least there could be more. Of course, the prolate stars do not have any radial node, and that's, again, evidence that they are indeed the ground state. But because the spherical stars initially were found with one radial node, the rotating stars that were initially constructed, they also had one radial node. And they had this Saturn-like morphology that you see here for constant energy density surfaces. But later, triggered by different motivation, the rotating Broca stars, without any radial nodes in the temporal component of the Broca potential, were actually found. And this seemed very surprising at that time, because the rotating stars didn't have any radial node, but the static stars, the spherical ones, had one. So why wouldn't the static sector have a no radial nodes? And the answer was, well, it does have no radial nodes, but you have to go away from spherical symmetry. And now we know the answer. These rotating stars, Broca stars without radial nodes, they are still believed to be the ground state of the rotating family of solutions. And in fact, they are known to be dynamically more robust than the spinning scalar stars, which are toroidal instead of spheroidal. In fact, when the boson stars, the scalar boson stars, were first found in the 1990s, they were called the mass torus in general relativity. But they, again, were, not much was known about stability all along the space of solutions, even before the maximum ADM mass. But it was found a few years ago that these rotating scalar stars, all of them in this mini model that is without self-interactions, they are all unstable. They break down against a non-axisymmetric mode. So this I can show you in a little, again, movie. So what you see here is the visualization of a fully nonlinear evolution of the Einstein-Klein-Gordon system in the left panel. The color code denotes the scalar field amplitude. So you see, you're seeing it from above. So you see it's a toroidal thing. And at some point, which is a moderately long time scale of the order of 1,000 light crossing times, there's a non-axisymmetric instability that kicks in, and an apparent horizon forms. You can see that in the right panel, where the mass associated to this apparent horizon is this blue solid line, and the energy associated to the scalar field is the green dashed line, which tends to vanish as it is swallowed by the black hole, signaling that there is indeed the black hole formation. So these stars, rotating scalar boson stars, all of them, they are unstable. Even the ones that would be or are in the tentative stable branch. There is no stable branch here. But this instability seems to be absent in these cousin Broca models. So the spinning Broca stars without any radial nodes, they seem to be dynamically robust. And this was supported by numerical evolutions with a timescale at least 10 times greater than the ones where the scalar instability is seen. So as illustrations here on the left panel, one starts with a spinning Broca star with a very strong perturbation that visibly changes its energy distribution. And then on the right panel, one starts with an excited spinning Broca star that has an energy distribution which is Saturn-like. And in both cases, the evolution approaches a spheroidal fundamental spinning Broca star without shedding away of the angular momentum, or all of it, and without collapsing into a black hole. So the conclusion is that spinning Broca stars are dynamically more robust in the simplest models, that is, without any self-interactions. The addition of self-interactions has an important impact on these conclusions, but I will not discuss that too much today. But for instance, in the scalar case, it can mitigate the instability and bring new regions where stars could be dynamically more robust. So to summarize, although the scalar and the vector boson stars have a clear parallelism in the existence of solutions, dynamically a surprising different picture emerges with the solutions selected by dynamics being quite distinct. So in the scalar sector, we have a spherical ground state that's dynamically robust, and there are dipolar solutions which decay, and the rotating solutions also seem to collapse. But in the vector sector, the spherical stars are not the ground state, it's a dipole, and the rotating solutions, which are spheroidal, are also dynamically robust. So it's very interesting to observe these differences, and there are probably deeper reasons for this, which one could discuss. But let me conclude this part on this discussion of bosonic stars by saying that the models that I've been discussing so far are single field. So you consider in the scalar case a single complex scalar field, or in the vector case a single complex vector field. But this single field bosonic stars can be used as building blocks for multi-field bosonic stars, constructing appropriate superpositions, which moreover can also change the dynamical properties. So for instance, it's known that excited monopole scalar boson stars, which excited means that they have radial nodes. This is in the scalar case. They are unstable against the decay into a fundamental spherical boson star, which has no radial nodes. It can be stabilized by adding a sufficiently large fundamental monopole boson star as a second field. So you build a kind of a hybrid state, and you stabilize the excited part. And in the same spirit, for the non-relativistic bosonic stars it's called the Schrödinger-Poisson system. This is the non-relativistic version of what I've been discussing. A dipole configuration is stabilized by adding a sufficiently large fundamental monopole. And these examples turn out to be illustrations of a stabilization mechanism that was discussed in this paper that I put here at the end, discussing also families of multi-frequency, multi-field bosonic stars. So this triangle that you see in this illustration is for a so-called L equals 1 family, which has 3 complex scalar fields. And depending on the relative amplitudes of these 3 complex scalar fields, you have different limits. For instance, you have a dipolar limit. You have also a limit where you have the single field kind of spinning stars that could be spinning in either way. And you also have an interesting limit in which all the 3 fields have the same amplitude, but they have different spherical harmonic kind of angular dependence. And you build these so-called L boson stars, which turn out to be spherical, even though the individual fields, they have some non-spherical morphology independently, but they combine themselves in a way in which the end product has a spherical morphology. So this is only one example of one such family. You can, and this is for the scalar case. Recently, people have been doing this also for the vector case. It's possible to build also these, say, L troca stars. And there's a lot of things to explore also on how these combinations can change the dynamical properties of this type of objects. So in the remaining time of my talk, I would like to tell you a bit more about phenomenology of these bosonic stars. And I would like to focus on the ability to mimic the phenomenology of black holes with current data, which I would like to call the imitation game. So I would like to give you 2 examples. And well, let's see how time goes. But the first example is related to gravitational waves. I would like to discuss the ability of bosonic stars to mimic a particular event, which is GW 190521, which was a very particular event. You might have heard about this. The progenitors in this event were estimated when it was announced as the most massive of any event thus far, about 85 and 66 solar masses for the two progenitors. And this means that within the uncertainties, at least one of them is in the so-called parent stability supernova gap, which is a part of the mass spectrum of black holes where, it's not expected that such a black hole could be the direct product of the core collapse of a neutron star, and because of the properties of the supernova. So this leaves the question of how these progenitors came to be, because even if it was a black hole, it was not an easy to form black hole by just this process. It could be, of course, a result of a merger, and people have speculated about that. And because it's a very massive event, it is a low-frequency gravitational wave signal, so you only see the very end of it in the current detectors because of the sensitivity band. So there is no in-spiral in the observed transient, and this leaves room to speculate about the true nature of the event. In fact, the event looks as much as a simple burst-like transient as the final part of an in-spiral, because it misses the clear chirp track that you see in those longer events where you have a few orbits. So this odd event is an invitation for alternative explanations, and one was proposed in this paper that we put out already a couple of years ago, where we analyzed this as a collision of spinning protostars. And doing a likelihood Bayesian analysis using the same libraries as the collaboration, the LVK collaboration, used for black hole binaries, plus an extra library of waveforms for protostar collisions, which I'll tell you about, gave a slight statistical preference to the Proca model. Furthermore, this analysis could determine the mass of the putative ultralight vector boson that was the composite particle, the particle that was composing these protostars, and gave a value of 8.7 times 10 to the minus 13 electron volts. So my point is that even if one completely rejects any physics reality of this scenario, the analysis illustrates the path from an exotic theory to real observation. So let me tell you how this was done. Given the dynamical robustness of the spinning protostar that we discussed, so here I'm doing spinning protostars, the ones that I told you they are dynamically robust. They can be collided in binaries. Now, the simplest such collision are head-on collisions. Considering this over, quasi-circular mergers is, of course, just the first step. It has technical advantages. And one may argue this is less astrophysical, which is true. But the point to be made here is that even then, the model can compete with vanilla black hole binary mergers used for GW 190521. So the simplest setup is this one that I'm illustrating here, which can be then generalized in many ways. You consider two equal mass m and equal frequency omega, perturbatively stable spinning vector bosonic stars. The spin axes are aligned. They are perpendicular to the screen, pointing towards each one of us. They are initially at the coordinate distance d in the x direction. They could have velocities vy in the opposite y direction, but here we take this to be zero. This is what is called a head-on collision. Quasi-circular binaries require sufficiently large vy. Now, with this setup, fully nonlinear numerical relativity evolutions of the Einstein-Proca system can be performed. So the bosonic stars, protostars in this case, have an eccentric trajectory due to frame dragging because they are rotating. So there's a frame dragging, so they don't actually collide head-on. They acquire a little bit of an eccentricity. Then they merge, and there's an apparent horizon that forms. So a black hole is formed within with a certain mass, MBH, and a certain non-zero total angular momentum, JBH. In the simplest collisions, the two stars are equal. So in particular, they have the same frequency in this harmonic time dependence that we saw, and the same mass. And we can then extract the waveform of the collision process. So if we vary then the stars that we take as the initial data, the waveform varies. And so I'm illustrating here a simple scanning of the parameter space as we vary the initial stars, which we label by the frequency omega, to be the ones indicated by the red arrow. The waveforms of the collision process, as described before, they also vary, which is shown in the upper panel. And in this scanning, we do not go to too high frequencies, otherwise the final object is not a black hole, and the signal is not compatible with GW 190521. And these examples are also for equal mass here. But we've also performed unequal mass collisions. And this is illustrated here in this slide. There's 4 different movies of waveforms, show how they vary when different initial data is considered, that is, when different colliding protostars are considered. So the first top movie, top left, is the same as in the previous slide, and the other 3 are for unequal masses. While in these equal mass collisions, L equals M equals 3 is almost completely suppressed, the mode, compared to the dominant quadrupolar mode with L equals M equals 2. In unequal masses, it can have a significant contribution, and that's what is being shown in red. So that's another mode. And these waveforms can be now used for gravitational wave analysis, data analysis, for injections, waveform reconstruction, parameter estimation, and potential searches as well. So there's a catalog with about 750 waveforms that was constructed already, all of these from numerical relativity evolutions. And potential searches is precisely what we did with GW 190521. So we can then study statistical preference using a Bayesian analysis, and this was done in the paper that I've shown you. This was led by Juan Calderón Bustillo, who's also a member of the LIGO Virgo Cagra and participated in the same analysis for LVK, for the standard interpretation of the event. And looking at this log base factor, there's different priors here, but I don't want to get into any details. The conclusion is that the base factor is slightly or even considerably better for the PROCA model. Also the best fits is given for the PROCA model. This statistical preference is by a factor of 2 to 30, so it's not too significant. But one can say that at least there's a degeneracy, and this is the point that we want to make with this imitation game. Of course, any further conclusions have to be taken with a lot of caution. But okay, following up on this, the statistical analysis gives us a probability distribution for the frequencies of the PROCA stars, which nicely fades out at the extremes of the range we've analyzed, which suggests we are in the right frequency range. And this gives a frequency distribution centered around a particular value. And this determines the m times mu of the PROCA star, the mass in units of the PROCA field fundamental mass, let's call it. Then if you identify the mass of each PROCA star as half of the mass of the final black hole, which is reasonable here because the inelasticity is very small. So the energy lost is in gravitational waves, its fraction is much lower than in spiral. So this determines then the mass of the ultralight boson. And so you can get this type of histogram for that distribution, which is centered around a particular value. So
you have 5 minutes. You have 5 minutes.
Okay, so I think I can finish this part, not tell you too much about the remaining, but then in questions. So to conclude using this PROCA model, we can use this event, real data, GW 190521, to infer the mass of the ultralight bosonic particle, which in this case is a vector particle. And this proof of concept shows how there can be degeneracy in real data between 2 very different models. But in order to see it, you have to do detailed phenomenology of non-Kerr models, because the searches are very much, based on having templates and therefore well-developed theory. And in this particular case, you can also get how much, you can also illustrate how you can extract physical information about a new fundamental particle, putative dark matter particle, from the data, making your gravitational wave detectors into a particle detector. And that would be, of course, a much more exciting possibility to have this type of scenario finding new physics. But a potential confirmation will require, of course, many more events, and future population studies, which are, I would say, possible within the next few years. And potentially a hint towards dark matter. So let me just finish this by telling you about a question of scales. You may be asking, so why not the other gravitational wave events? Why could this event be such a protostar collision and not the other gravitational wave detections? Well, as you may remember, the mass of the ultralight bosonic particle determines the maximum mass of the corresponding stars. So in this case, this turns out to be about 173 solar masses. All other events prior to this one, they corresponded to final smaller masses. So since the other events are compatible with black hole formation, with the evidence of a ring down, these cannot be Procus-star collisions. For the Procus-star collision to form black holes, they have to overshoot this limit, which was only observed, at least until this event was reported by this event. And this is interesting, again, as a proof of concept to illustrate how a new scale can impact on data. Of course, this could be now repeated for other events. There's some other events that have appeared that this analysis has been repeated, and we've reported it in a subsequent paper. Now, I don't think I have much time for what I would like to tell you about the imitation game with shadows. So I can keep that for a discussion if necessary. I would like to say that, of course, there's this other observable called the black hole shadow that we take as evidence of, black holes. But again, these bosonic stars give us interesting examples where we can have interesting degeneracies, given also the limited information in the current data. And this could come from several different sources, different physical properties of the, say, geodesic motion around the bosonic star. I had two examples, one related with the fact that time-like circular orbits around the bosonic star can have a property that you do not see in black holes, which is the existence of a maximal value for the angular velocity attained at a certain radial distance. And this could actually give rise to some an effective shadow, and I can explain afterwards if you'd like. And the second thing is, if you have something that has a non-trivial geodesic structure, and for instance, this is an example where you have different disconnected regions in the space-time where there can be circular time-like geodesics and gaps between them, and this occurs also for dynamically robust Procus stars, you could have, if an accretion disk accumulates in those regions, features that again imitate, observations of a black hole. So this was very brief. I would like to just conclude by telling you that bosonic stars illustrate theoretical possibilities of dynamically robust black hole imitators that could manifest themselves only at some specific scales, and that producing detailed phenomenology will constrain the model and the corresponding exotic physics, or in the best case scenario, provide a smoking gun to this new physics. So with that, I will conclude, thanking you very much for your attention.
Thank you, Carlos.